Good morning to all of you. I hope you all can hear me. My voice is clear to you and you can see my screen clearly as well without any interruptions. Let's start with today's work. We have some practice problems lying up on thermodynamics. So I will take up some of them and then we will meet in today's practical. So going ahead, I will be presenting my first problem for the day, that is here in front of us. Let me enlarge it a bit so that we can read it even if you are reading it on a small screen, and then we can go ahead and solve it. Van der Waals equation of state, an approximate representation of behavior of gases at high pressure, is given by this equation: P plus a n square by v square into V minus NB is equal to nRT, where N is the number of moles and A and B are constants whose values differ for different gases. If you put A and B equal to 0, then this will reduce to ideal gas equation. So what happens that is a real gas? You are all familiar with bit of theory. Let me put it in perspective. If you are talking about real gases, then there are intermolecular forces of attraction, and because of that, the pressure measuring device actually measures a pressure which is less than the ideal gas pressure. So that pressure correction is needed. That pressure correction term is A n square by V square. Do remember that corrected term is inversely proportional to the square of the volume. Now similarly, each gas molecule, remember ideal gas, theory of ideal gas assumes that the volume of individual molecule is negligible, but this assumption also breaks down when the molecules are large in size or when there are too many molecules in the given volume. So the actual volume available to the gas would be less than the volume of the container. So this is a negative correction. These two corrections put together what we call it as van der Waals equation of state. So we are going to use this. Calculate the work done by the gas with this equation of state in an isothermal expansion from V1 to V2. For ethane C2H6, A and B are given. Calculate the work done by 1.80 mole of ethane when it expands from 2 into 10 power minus 3 meter cube to 4 into 10 power minus 3 meter cube at a constant temperature of 300 Kelvin. Do the calculations using van der Waals equation of state and the ideal gas equation of state, and for which equation the equation of state work done is larger and why should it be so? So that's a very straightforward questions. Let's take it in some steps. So I will first write my first equation here, which is van der Waals equation of state. It is P plus a n square divided by v square V is the volume, bracket V minus NB, and that is equal to nRT. So that becomes my van der Waals equation of state. How do I get my work done from this? What is the work done equation? So we are all familiar. Work done, differential work done is PdV, and the total work done W is going to be integration of PdV starting from V1 to V2. So I need to figure out how would I carry out this integration in this. I need to find out P, and for that I need to rearrange the terms in this equation. So if I rearrange, V minus NB can go in the denominator, and an square by V square can go on that side as a negative term. So my work done will be equal to, I put my integration, say it says it expands from V1 to V2, and now here first is this term, so it will be nRT divided by V minus NB, okay, that is the first term. Now this will go as this side, it becomes a negative term, so it will be minus, then you write that negative term an square divided by V square, and I can put everything in bracket and put the dV term here. Now what will be this integral? So most of you are math student. You are champion of solving these little integrals. So I will not get into those details of solving. You look at it. This is nRT. It says it's an isothermal expansion. So nRT is constant. So I can write nRT outside. I don't have to worry about it. Then it is integral of 1 over V minus NB. So let me just write this term also. So V1, V2, and 1 over V minus NB. This is my first term. I will bring dV also here. I will open the bracket minus, and this is my second integral V1, V2, and an square is a constant. It could have gone out. So I will write here in small letters an square, and what you are left here is 1 over V square dV. How do you solve this? So very straightforward. Now you can see that this is a log and this is 1 over V square, so that can be solved easily. So the work done is nothing but nRT, and remember this is log of v minus nb, but we will take the put the higher limit and then lower limit. So if you do that in the log and subtract, you get a ratio. You will get v2 minus nb. This is the numerator term divided by v1 minus nb, and this is the denominator term. So this is nRT log, this is the first term integral. Now this will become, when you take an integral, this will be v power minus 2. When you solve, it will become v power minus 2 plus 1 divided by minus 2 plus 1. You get a minus 1. That will make this as plus a n square as it is. And you will get 1 over v term. When you put the values, it will become 1 over v2 minus 1 over v1. So this becomes my work done. Very straightforward calculation it was. Now calculate the work done W in case of all these values are given. You can see N is given, V1 and V2 are given, A and B are given. So, and temperature is given. So almost all the values are given. You can substitute it in this and calculate. I have already done this calculation. So I will just, if you do this as van der Waals or real gas assumption, which I'm doing here right now. I should not have bothered, but yeah, this is the real gas assumption. So work done for real, this is a common equation. So now if I put all this, the value that I will get is 2.881 or something into 10 power 3 joule. This is my value obtained here. Now what is the work done in ideal gas? If I assume that it's an ideal gas, then how much work will I do? What is my formula? You again take this same thing, but instead of P being replaced by all these, it will be replaced by nRT by V. So the integral is simple. Work done in an ideal gas situation, you are all familiar, is NR isothermal work done in an ideal gas. We have discussed in the last class nRT ln V2 by V1. So if I use my values in this equation, the answer that I got was 3.1 into 10 power 3 joule. So that becomes my work done. Now, which one is doing more work? So obviously, in case of ideal gas, the work done is more, expansion happens more. Remember, work done is a measure of expansion. So what we do is, in ideal gas, the expansion will happen more. Why would it happen more? Very simple. There are no intermolecular forces to hold the molecules back. Therefore, the expansion will always happen more in this case. So that is your answer. So let's go to the another problem which I have picked up. This is a typical problem. Few of you might have solved it and few of you might not have. but people find this confusing, so I have selected it. Let's go through it and solve it quickly. So I have enlarged the problem for you people to read it. Please read it once. A lot of calculations are involved in this. We have to be careful. An insulated container of negligible mass holds 0.6 kg of water at 45 degrees Celsius. You put a 0.05 kg ice cube at minus 15 degrees Celsius in water. Calculate the final temperature of water once the ice has melted. Calculate the change in the entropy of the system. So this is, if I have to draw, then you have some ice cubes here which are zero point 0.6 kg, sorry, which is 0.05 kg. So rough diagram sometimes helps. Here it is not needed much, but I am drawing 0.05 kg. And remember the accuracy is given up to 1, 2, 3, 4 decimal places. So please be careful. All your answers should proceed that way. And this is point, you have a water in container. The amount of water in the container is, I am not writing this whole thing because it is still not very convenient to write on keypad, but still. So K on the water is 45 degrees. So this fellow is at 45 degrees Celsius, and the ice cube is at minus 15 degrees Celsius. So yes, then you mix them into one. So from this situation, what you go do is you go in another situation where you put both the things together, and you have to find out what is the final temperature. So in this case, you will have to worry about whether the ice has melted or not. If it has already melted, then you have to make your calculations, and if it is not, then you will have to retweak it. Now, you know that the principle that applies here is the conservation of energy. What it means? It means the amount of heat given by the water has to be equal to amount of heat absorbed by the ice. So that principle we use, and we can make some quick calculation. Remember, I will assume first that the ice will melt. I have a significant clue to think that way because ice mass is very less, 0.05. Water mass is zero point 0.6. So it's very large mass of water. Although also, if 0 degree Celsius is the melting point, then you are at a much warmer side. Water is on the much warmer side, 45. Ice is not that cold from 0, minus 15. This is 45 degree. A large mass is at a larger temperature above the 0 degree, while a small mass is at a smaller temperature below 0. So chances are that the ice has melted. So I'll start with that and do my calculation. If my assumptions will be incorrect, my answer will turn out to be negative. Remember. So the how much heat the ice will absorb. So the ice will absorb, in fact, three heats in three parts. First, ice is at minus 15 degrees Celsius. So from there its temperature will rise up to 0 degrees Celsius. So in this process the ice will absorb heat. Then at 0 degrees Celsius the phase conversion will happen. If the phase conversion happens, the ice will absorb heat once again in that process. And then after that, the as the after phase conversion, remember when the phase conversion is happening, the temperature will remain at 0 degree Celsius. After the phase conversion, the temperature will rise and it will attain some common temperature. So again it will gain heat. So the ice heats into three parts. One from minus 15 to 0. Second, phase conversion at 0. Third, after it has converted into liquid, then again from 0 to some final value of temperature. Water will lose heat from 45 degree to that some final temperature, and that is what is our assumption. And we have to calculate the final temperature. So I will know that if there is a change in the temperature, then the formula that we use normally is dq is equal to mc delta t. And if there is a state change, then the formula that we normally use for the heat absorbed or given out is M into L, where symbols have their usual meaning. C is specific heat, delta T is change in temperature, M is mass, L is specific, sorry, it's a heat of, in case of melting point, it is speed, it is the heat of fusion. So I can use these two. So let me just simply straight away write the value. First, the ice uh, melting, ice heating up from minus 15 to 0 degrees Celsius. So it will be M, I will use this M, so 0.05 into specific heat of ice. Remember, specific heat of water is 1 calorie per gram. For ice, I think it's slightly more than 1 calorie, 1.1 or something. But here I will ignore that difference. If you want to be more specific, you can recalculate. So I will take specific heat of ice same as specific heat of water. So again 1 calories per gram, which is nothing but, I want in joule here. So it will be 4.2 into 10 power 3 joule per kg. Remember here, so 10 power 3 will come into, I will calculate my third term, delta T. Delta T is change in temperature, so final temperature is 0, initial temperature is minus 15, so the change in temperature is 15. Remember, it does not matter, since you are calculating a change in temperature, it does not matter if you use Kelvin or degree Celsius. So this is the term or the amount of heat that the ice will take to raise its temperature from minus 15 to 0. Now it will melt at 0. So for melting it will absorb this much amount of heat. So again I will write 0.05 into L. Now latent heat of fusion for ice is 80 calorie per gram, which you multiply by 4.2, or to be strict 4.18, and calculate it on a per kg basis, then it will turn out to be 3.34 into 10 power 3. I will write it as 334 into 3.34 into 10 power 5. I will write it as 334 into 10 power 3 because this is also in the order of 10 power 3 plus. Now here ice temperature has raised from 0 degree to 15 degree, sorry, from minus 15 degree to 0 degree. Here ice has melted. Now after melting, the temperature will again rise to some final temperature. So I will have to write that term as well. So it will be 0.05, mass remains the same. As I said, now it is water, so it is specific heat of water 4.2 into, and remember, as I have already told you, that here I'm also using the same as specific heat of water. If you want to be more correct, you can use specific heat of ice and calculate into, now the final temperature assumed to be T. Now it is rising from 0, so T minus 0 will give you T. So this is the heat absorbed by ice. So this is delta Q by ice. Okay, how much heat the water will lose? So the water was at 45 degrees Celsius and mass is 0.6 kg, so I can use this once again. So it will be, I will write here as 0.6 kg m into this very term 4.2 into 10 power 3 into, now how much is the temperature? So initial temperature is 45 and final temperature we have assumed as T. So 45 minus T is your final temperature, and this is heat absorbed by the water. So now these two parameters has to be same. Heat given out and heat absorbed has to be identical. So you can equate this with this and solve. If you do that, I've done this calculation, my temperature of the mixture comes out to be 34.64. This is my temperature of the mixture that turns out to be. Now, coming to the next part, calculate the change in the entropy of the system. So again, how do you calculate the change in the entropy? So let me recall the entropy formula. You know that the entropy formula, entropy is a change in the entropy, ds is defined as dq by T. So if the temperature is constant, we use this formula. So at phase change, temperature is constant, so I can use this formula to calculate entropy. But if the temperature is changing, then I need to take an integration of this. An integration of this will give me a finite change in the entropy. So finite change in the entropy will be equal to integration of dq by T from T1 to T2. Okay, now I can dq can be written as mc dt, and m and c can be constant, so they will come out. So dt by t, so that will give you m c ln, and remember the limits were t1 to t2, so this will become t2 divided by T1. That is how you will calculate your entropy when there is a temperature change in the phenomena. And this is the way you will calculate the entropy if the temperature is constant. So here first temperature is changing, then constant, then changing. For water temperature is changing. So three places temperature is changing. So you will use this equation for 3 times, this for once, to calculate the change in the entropy. So how do I calculate my change in the entropy? Very straightforward. My first water is heating, ice is heating up from point 0, from minus 15 to 0 degree. So that is my first part of entropy, delta S1. Let me just write it together. So that is my first part of entropy. So I may write 0.05, and this is the change in the temperature. So into m into c into 10 power 3 ln t2 minus t1. So ln, and remember here you need to convert things into Kelvin. So 273, remember the final temperature is 0 degrees. So 273 divided by initial temperature is 258, that is minus 15 degree. So if you solve this, you get the entropy change as 11. So I leave it here, and then I take the next term, which is the phase change. So for the phase change, I can simply write dq by t. dq by t is Lm by t. Now L I know is, as we have discussed, 334 into 10 power 3 into 0.05 divided by 273, and the last term, when the ice after melting heats up to 34.64 degrees Celsius, so that will again use the same form, 0.05 into 4.2 into 10 power 3. But now your initial temperature is 273 and the final has risen 307. I should have left all these calculations for you people, but nevertheless now I've done for this particular problem. So these are all my 3 entropies for the water, for the ice. For water, the entropy would be, what would that be? So for water, So let me put another one. For water, the mass is zero point 0.6 into 4.2. Entropy calculations are a little tricky, so I decided to do it here for you people. This is 10 power 3. Again, that water's temperature is changing, so you will use this equation. Remember, the initially it is at 45, so initial temperature is 318 Kelvin, and the final temperature is 307.64, which I have used here also. 64, not 5. So put all these things together, you will get a total change in the entropy. So the total change in the entropy, after you will evaluate, my calculations show results which are interesting. This is around 11.86. This is around 61. Maximum entropy change happens in this. Remember, because the breaking out from solidified to liquid phase, so disorder is increasing. Then 25 here, and this is negative. Remember, the numerator is smaller than the denominator. So take a natural log, it will give you a negative number. So to subtract. So if you put all these things into perspective, the answer you get is 14.46 with whatever SI units. So that is the total change in the entropy. So this is an interesting question which we took. Now let me introduce one more at least. Maybe we will solve it in the next class. The problem that I can introduce now is on the heat engines or a dynamics of a thermal plant. Remember, maybe around 10 years back, there was a proposed nuclear power plant in Ratnagiri district in Maharashtra, which was opposed by environmental activists. The kind of environmental activism is there everywhere these days. So they are opposed by environmental activists by tooth and nail. Eventually, it was scrapped. India lost a lot of money in that process. So typically, an environmental activist will sit and do these kind of calculations. The kind of calculations are put over here. A typical coal-fired power plant generates 1000 megawatt of usable power at an overall thermal efficiency of 40%. What is the rate of heat input to the plant? The plant burns anthracite coal, which has a heat of combustion of 2.65 into 10 power 7 joule per kg. How much coal does the plant use per day if it operates continuously? At what rate is heat ejected into the cool reservoir, which is the nearby river? The river's temperature is 18 degrees Celsius before it reaches the plant and 18.5 degrees Celsius after it has received the plant's waste heat. Calculate the river's flow rate in cubic meter per second. By how much does the river entropy increase each second? So that is our problem. But I think with this introduction to this problem, I can stop. Maybe in the next class we will take this problem and then further. In the next class also we will focus on the problems on thermodynamics only. We can stop here. Thank you.